root locus, and we have seen the magnitude criteria and the angle criteria. The other conditions with the root locus which we have covered is we have seen the starting point of the root locus, and we have seen that root locus always starts from open loop poles. And before describing all these things, we have seen why there is a need of root locus, and it come out root locus is required to check the relative stability. So today we'll see the methods or the rules to make root locus. There are certain rules by which we can make the root locus for any given transfer function. So I'll take all these roots one by one. So of course the first rule for the root locus is starting and terminal points of root loci. As we have seen in the previous class, root locus always starts from open loop poles, and for the terminal points, root locus always gets end up on open loop zeros. Now let's take one case over here. Let's take an example. The open loop transfer function of the system is this. Now let's start making the root locus for this one. On the S plane, we have taken one open loop 0 at -1 and two open loop poles at -2 and -3. Now here, for this given particular example, we have two poles and one 0. And according to the first rule, your root locus starts with the open loop poles and it gets end on the open loop zeros. But as we know, for the given particular example, we'll have two loci because we have two open loop poles over here. So that's why we'll have the two different loci for each pole. Now here we can see that one pole can easily get end up to this given 0, but the second pole does not have any open loop 0 to get end up. So as we have discussed during the network class, that number of poles and zeros always remains same. If for the given particular system transfer function like this one, the number of poles are 2, this physical number of poles are 2, but there only one physical 0 is given, so the other 0 exists on infinite, and it is same or vice versa. If there are two number of zeros and only one number of poles, so the other pole exists on infinite. But for the most of the practical system, your transfer function always have more number of poles than 0. So now it is clear that this pole, both the poles are going to end up on the zeros, and one 0 exists at -1 and the other 0 exists on infinite. So one pole is going to end up on -1 and the other pole is also going to end up on 0, which exists on infinite. Now with respect to this example, now let's take the second rule. The rule number 2 is root locus on real axis. As we have discussed in the previous class, to find out any point on the root locus, we always use the the angle criteria. If any point, any arbitrary point on root locus satisfies the angle criteria, that means that given point is a part of the root locus. So now here we have taken one example, the previous example where we have one 0 at -1 and two poles are at -2 and -3 respectively, and we want to see the which segment is part of the root locus, whether this segment will be the part of root locus or this segment will be the part of root locus or this segment will be the part of root locus, and this which is going towards the minus infinite, whether this segment will be part of the root locus. Now let's suppose one arbitrary point over here, and to check whether this given point will be the part of root locus or not, we'll use the angle criteria. Now let's draw the phasor from all the poles and zeros. This one, from this pole, this, and from this pole is this one. And as we can see, the angle made by 0 is 0 degree. Angle made by the pole at -2 is also 0 degree. And angle made by the pole at -3 is also 0 degree. So the sum of the angles made by poles in 0 remains 0 degree. And it does not satisfy your angle criteria, which is nothing but 1 plus minus 180 to k plus 1, where k varies from 0, 1, 2, and so on. So this point is not going to satisfy your angle criteria. So this is clear, this point is not the part of the root locus. Now if I'll just take one more arbitrary point just next to this point over here, and again if I'll draw the phases from all the positive zeros, again it will give me the same angle and will not satisfy the angle criteria. So this segment, any point on this segment is not going to satisfy your angle criteria. So this segment is not a part of the root locus. Now let's take any or one point on this segment between -1 and 2. I have taken this point over here. Now let's draw the phasor from 0 this side, from this pole this is side. Angle made by 0 at -1 is 180 degree. The angle made by pole at -2 is 0 degree. Angle made by the pole at -3 is 0 degree. And sum of the angle is coming out. So any point between the segment -1 and 2 on this segment, any point will have the same angle and also satisfies the angle criteria. So that means all the points on this segment is going to satisfy your angle criteria. So this will be part of the root locus. Now again let's take one point between the segment -2 and -3. Now here for this segment -2 and -3. Now let's take one point over here and draw the angles. Draw angle from 0 placed at -1, draw angle from the pole placed at -2, and draw a phasor from -3, and angle made by 0 placed at -1 is 180 degree. Angle made by poles -1 degree, and angle made by pole at -3 is 0 degree. And sum of the angle made by zeros and poles, 180 degree minus 180 degree plus 0 degree. So all the points on this segment will have the angle 0 degree and does not satisfy the angle criteria. So any point on this segment will not be part of the root locus. Now let's take point on this segment. I have taken one arbitrary point on the segment between -3 and -infinite, and let's draw the phasor from all the points. I have drawn the phasor from -3, -2, and -1. An angle made by 0 placed at -1 to this point is 180 degree. Angle made by pole placed at -2 to this point again is 180 degree, and angle made by -3 again it is 180 degree. And the total angle, summation angle made by poles minus summation angle made by zeros, is coming out again 180 degree, because it is angle made by poles, summation of angle made by poles minus summation of angle made by zeros. So this is made by 0, this is made by poles. So 180 plus 180 and minus 180 is equals to 180 degree, and it satisfies your angle criteria. So any point on this segment from -1 to -infinite is going to satisfy your angle criteria, and this segment will be part of the root locus. Now let's say what we are having now. So we have taken this example, and we have also discussing the rule number 2. We have 1 0 at -1 and 2 poles at -2 and -3, and we have also seen that this whole segment will be the part of the root locus, and then this whole segment will be the part of the root locus going towards the -infinite. Now this gives us the rule number 2, which is a point on real axis lies on the locus if number of open loop poles plus 0 on the real axis to the right of this point is 0. So if we're talking about this point, any point on between -1 and 2, and if we'll see to the right of this point, the total number of poles and zeros should be in odd number. So this point, any point on this segment, if we look up to the right, we have only 1 0, so it's the odd number. And if we look for this segment or any point on this segment, to the right of this we have one pole and one zero, which makes it even number. Total number of poles and zeros are even. And if we look for this segment, and if we look to the right of segment or any point on this segment, we have two poles and one zero, so it makes it an odd number. So this will be the part of the root locus. So now it is very much clear. The rule number 2 says that a point on the real axis lies on the locus if number of open loop poles plus 0 on the real axis to the right of this point is R. So this is your rule number 2. Now it is very much clear that of course we have two poles, so we are going to have the two loci for this given root locus, and this pole is going towards, we can directly say it is getting end up on the 0. So the direction of the loci will be this, because root locus always starts from open loop poles. So it is originating from the poles, so direction will be from the poles, and this one is going towards the 0, getting end up. So this loci is complete, and as we know, this loci is going towards the infinite. So this loci is going towards the infinite. That means the other 0, which is not given in the example, exists on the infinite. So this loci is also going towards the 0, which placed at. So this makes complete root locus for the given example, which was the open loop transfer function was k s plus 1 divided by s plus 2 and s plus 3. For the next session, we'll take more complicated example and we'll see the remaining rules related with the root locus, where we'll have the breakaway point. We'll also say centroid and asymptotes for the poles which going towards the infinite, and root locus on imaginary axis, and departure and angle for the complex poles. So I would suggest please go through with these points which we are going to take in the next session of the control system class. Thank you.